Hi, this is Professor Nathan Smith of Fresno Pacific University. This video is from my students in Econ 301 in Visalia in North Fresno. It's on Chapter 6, Demand Forecasting. Now, in the last chapter, we talked about demand estimation, but specifically we looked in general at the idea of regression analysis, and we got into some somewhat technical mathematical material, maybe more technical than people are likely to fully absorb, and something we usually rely on computers to actually implement for us. But we talked about minimizing the sum of squared errors in order to find the regression line, the line of best fit. We talked about hypothesis testing, how you figure out whether a regression result is statistically significant. This chapter is a little bit more applied. In some ways it's a little bit ad hoc, in the sense that you're looking at techniques that might be of considerable practical value, but not of perhaps the same kind of general interest. But nonetheless, they will sometimes be derived from or sort of use the more abstract technical approaches that we discussed in the last chapter. So to begin with, you can distinguish research of all sorts into quantitative and qualitative, and it's not always a perfectly clear distinction, but it more or less works. We're going to focus mainly on quantitative, but just to start with, introduction, qualitative forecasts. Think about if you're interested in what's going to happen to demand. Is it going to increase? Is it going to decline? Is it going to increase among some demographics and decline among others, and so on? What are the trends? So one way to do this would be survey techniques. Now, a couple of these the first examples of survey techniques: planned plant and equipment spending and expected sales and inventory changes. These are more suitable for firms that are kind of upstream, maybe not selling directly to consumers. So it's if you're selling machinery, if you're selling software, you might be interested in basically what businesses are planning to spend money on, and so that could depend on their equipment spending, their investment plans, or if you're producing intermediate goods. So if the demand for your good is a derived demand, it depends on demand for some other good that's further upstream, that's when you might look at expected sales. How much do firms expect to sell? What kind of inventory changes do they expect? That will affect their demand for your product. If you're selling directly to consumers, you might conduct surveys about consumers' expenditure plans. But again, we already talked about the weaknesses of survey techniques in general. Particularly with consumer expenditure plans. People find it pretty hard to predict what they're actually going to produce. Firms may be more rational, maybe they are somewhat systematic in their investment, or in predicting what their sales are going to be. So maybe they can give you somewhat reliable answers, but in general, survey techniques definitely have limits. And a lot of times people will be biased. People might, if you ask them how much beer they drink, they might underestimate that. If you ask them how often they go to the gym, they're likely to overestimate that. Similarly, firms, I don't know, it wouldn't surprise me if they'd be even worse in some ways. They might be quite optimistic about what expected sales are going to be. Or they might tell you their optimistic estimates, even if they have some worry. You can do opinion polls. You could poll business executives, but business executives very often get it wrong. I mean, they might be experts in some sense, but they're certainly prone to being over-enthusiastic, and they may also not necessarily want to divulge all the information that you want to know. You could poll your firm's sales force, but they may also have their own biases, and at the end of the day, they don't have a crystal ball. They can't see the future. Consumer intentions, but then again, consumers may not be that reliable of predicting their own demand. So there's weaknesses in all these approaches. They might be worth doing, but it's definitely nice to sort of know some of the quantitative options as well. This is this table is just basically meant to drive home the idea that that demand can be subject to big swings, and those swings are important, or there can be a lot of unexploited demand. In this case, in the course of a decade, McDonald's nearly quadrupled the number of restaurants in Japan, nearly doubled the number in Canada, and in Britain more than doubled the number in Germany. These are huge swings in the number of McDonald's restaurants, and in just a 10-year period. You can imagine if they'd been conservative and didn't want to open new restaurants at that rate because they doubted the demand was there. It's sort of counterintuitive that there'd be this much demand. Well, they've also estimated market potential, and in Japan in particular, they figure there's even more than what they've exploited so far. Germany, they figure there's a lot more, or in France as well. So it's nice to be able to find out if there's a lot of latent demand for your product. Okay, so now we're going to get into something called time series analysis. Time series analysis is where you're tracking one variable over time. The example that we looked at in Chapter 5 was kind of a time series analysis too. We had a series of years and we were comparing sales revenue and advertising expenditure, but we didn't analyze it using techniques that are specific to time series analysis. In fact, we didn't even take time into account explicitly at all, which I think was sort of a mistake. I mean, from the point of view of it actually being good empirical practice. But if you do start thinking explicitly about time, there's a bunch of different things that might be going on. So first of all, there could be a secular trend. This is a long-run trend, either positive or negative. Second, you could have cyclical fluctuations. So a lot of times this would be correlated with the general state of the economy. If the economy is doing well, people will buy a lot. If the economy is doing badly, people buy less. But it could also be something specific to the industry for whatever reason. People buy a lot of cars and then they don't need as many new cars, and then after a while their cars are getting old, so they buy more. That could potentially happen in cycles as well. Even fashion might have its own cycles. There could be various sources of cycles. Seasonal variation. So many goods are more suitable for some seasons than others. So if you're in the ice cream business, probably your demand is going to decline quite a bit in winter. If you're in the snow shovel business, you'll definitely expect an increase in demand in winter. For clothes, obviously, different times of the year. Food to some extent, vacations, and there are a lot of goods that would have this seasonal character. And retail Christmas tends to be quite different from other times of year. So there are regular occurring fluctuations that specifically deal with the seasons of the year. And then there can be other influences this doesn't capture all of them. There's some that are sort of irregular or random and difficult to summarize under any of these headings. Okay, so the top chart here, this gives you an example of, first it shows a secular trend. So that's what a secular trend looks like per se. And that's kind of, you'd be unlikely to see a data series that really looks just like this. Well, it's just an exact straight line. Probably you'd see something that's much more fluctuating. The other curve that's shown here, but you would be able to kind of deduce that there's that trend like underneath, along with many other influences that would cause short-term variations. Now, we also see a cyclical fluctuation here. And in this case, the cyclical fluctuation looks a little bit like a sine wave, or like waves on the sea, or like day and night, or like seasons, lots of different cyclical phenomena in nature. It looks a little bit like those. But it's actually superimposed on a secular trend. So if this is what the data looked like, then the best analysis of it would be, okay, well, there's cyclical fluctuations, and there's a secular trend. If you didn't take the secular trend into account, then you'd probably make mistakes. You want to recognize both those phenomena and then incorporate that into your analysis. So the lower chart, in some ways this might look similar, I mean, in the sense that you've got this sort of cycles, but in this case the cycles more specifically are seasons. You've got quarters 1, 2, 3, 4, demand goes up, demand goes down, demand goes back up. Sorry about that. And in this case the blue series actually shows sort of like raw data, and then the seasonal variation. This would be an attempt to discern a seasonal pattern that sort of explains the movements in the raw data. Okay, so we'll start by thinking about trends. And trends, it can take a couple of forms here. You might have a linear trend. The linear trend is sort of the simplest to think about. So the linear trend would say that the quantity, the kind of underlying value of the quantity, grows by some value b every period. So that's easy to understand. But in most cases, it's probably more likely that the growth rate will take a little bit different form. It'll probably take a form something like this. Take the form of a constant growth rate. So you notice in this case, it's not that it increases by b each time, that it multiplies by 1 plus g, by 1 plus some growth rate in each period. G then is the growth rate. So G tells you that if G is 5%, for example, that the quantity is typically going to be 5% higher in each period than it was in the previous period. So, now, if you remember, this might be too subtle for you to have picked it up, but the models that we used last time, when we were running regressions, we would estimate a model. The models were always linear. So we found the slope coefficient. That implies linear. It's the slope of a line. And so there's a sense in which if we want to actually estimate this constant growth rate, that's going to be a problem. If we want to do it using regression analysis, that'll be a problem because 1 plus g to the t multiplying by 1 plus g to the t so the t is the exponent, that's where t comes in. That's not a linear relationship, and so we're not going to be able to estimate that. Fortunately, there's sort of a trick. We use the natural logarithm function. The natural logarithm function has this ability to sort of remove exponents. It turns multiplication into addition, and it turns exponent into multiplication. So you notice that in this constant growth rate function, you got st. Okay, that turns into ln st. So that's just you're applying the ln function. S0 turns into ln S0 as well. And you notice that S0 was multiplied by this 1 plus g to the t. The multiplication turned into addition. The exponent turned into a coefficient. So taking something to the power of it, power of t, and this when you apply the ln, it turns into multiplying something by t, namely multiplying this 1 plus g, but the log of that. So this is just applying lns to both sides. If this is true, that's the nature of manipulating equations. If you do the same thing to both sides, then the equation remains true. But this is linear, and this you could run a regression to figure out what, well, in particular, I guess what g is. So that would be how you would project a secular trend assuming a constant growth rate. Now, how often is it that the secular trend is really going to continue for a long period of time? I mean, if the trend continues for a short period of time, the linear trend and the constant growth rate trend are almost the same. If it continues for a long period of time, those start to diverge more and more. But how likely is it that a trend will continue for a long period of time, especially if it's a dramatic trend of 10% growth a year or something? Well, that's hard to say. I mean, you'd need a lot of industry knowledge to judge in particular cases. But I'd also say, in some ways, these methods are a little bit crude. They're kind of rough mathematical extrapolation. I mean, the goal is that they're better than if you were just making a judgment call yourself, but they definitely they have their limitations, and some of them more than others, and in some situations more than others. Okay, we've looked at secular trend. Now we'll look at seasonal demand. Really, demand for something that changes seasonally. So in this case, the good we're looking at is electricity. And we've got 4 years worth of data, 2007 through 2010. And we figure there's a secular trend here, since there may be a secular trend. There may also be seasonal effects, and if you look closely, you can probably see what the seasonal effects are. So, quarter 1, 11, quarter 2, 15, quarter 3, 12, quarter 4, 14. Quarter 2 and quarter 4 are higher than quarters 1 and 3. The same is true in 2008. So quarter 2 and 4 are higher than quarters 1 and 3. Same is true in 2009. Same is true in 2010. The second and fourth quarters are always higher than the first and third. Furthermore, there seems to be a secular trend as well. I mean, all the values in 2010 are at least as high as, and in most cases higher than, all the values in 2007. So, and there seems to be just a consistent rise in this variable. So you have a secular trend and you have seasonal fluctuations. Okay, now this plot, here we plot the data. And if you ignore if you go out to 2011, which is where you're making your forecasts, and you ignore the points that are below and above the line, which we'll see how those are calculated later, let's suppose you just ran a regression through these points and then you could assume the trend is going to continue. Well, these are the predictions you would make. 1, 2, 3, 4. They're all along the line. Well, that might be better than nothing. But it's not very accurate, really. Let's say it's unlikely to be particularly accurate because it ignores the seasonal variation that's going on. So how do we deal with the seasonal variation? And whether there's really some strictly best method, I don't know. This is kind of a rule of thumb that sort of does it for you. The ratio to trend method. So the first step here is that you calculate a trend forecast. So you'd run a regression and then you would predict the value of the variable for future periods. Then, sorry, not for future periods, actually for past periods. Sounds funny to talk about predicting it for past periods. I guess it would be better to say maybe not so much that you're predicting it, but rather that you're identifying what the trend was. But in any case, you have your trend forecast for you can construct the trend forecast for each past period. Then you can see what the actual result was, and then you can see the ratio. You can calculate the ratio. You notice if there's some season in particular which has particularly strong demand for electricity, then the actual would usually be above the forecast. And forecast is just a line going through all of them. And so the actual would be above it and you'd get a higher ratio. If the actual is lower, you get a lower ratio. And so then for each seasonal period, then you calculate the average of these ratios. Then you calculate your adjusted forecast by multiplying the trend forecast by the seasonal adjustment. That's probably not going to be very clear just hearing it in words or even seeing it on the screen, but we'll go through it and it might make it somewhat clear. Okay, in this case, we have season 1, so the first 3 months. You have the actual values for each of those years, 11, 12, 14, 15, pattern there. Then, if we look at the trend forecast, that gives us these values in column 2. To calculate the actual over the forecast. You notice there's not a lot of variation in these. 8.8, 0.95, 0.865, 0.906, 0.881, Probably there's just some technological reason that doesn't change much from one year to the next of why people are consuming less electricity in the first quarter. And we do the same thing for the others. Calculate the forecast trend, calculate the ratio of the actual to the forecast, and so on for the third and fourth quarters. Okay. Now, if we're average 0.887, this actually just sort of expands on the same thing. So you say trend forecast for 1996. So now we're actually projecting much further back. So we were looking at 2007 to 2009. They substitute different years. I'm not sure why. Maybe they were taking real data and then move the years up to fit a present example. But however that may be, then this is an example. Maybe this is what the real data was. They calculate the seasonally adjusted forecast for the first quarter of 1996 based on years 1992 to 1995, and then they get this value of 6.5. Okay. Okay, so that's seasonal variation. Now we'll move to moving average forecasts. And again, this is, in some ways, it's kind of a crude method. You're basically just saying, okay, well, what happened to the last W, some arbitrary number, so last W periods prior to the forecast data point. So, so if there's some, I guess it would be, T. So we're interested in time T. Trying to forecast some value of some variable for time T. You know the values from past periods. And so what we do is we say, okay, iterating with I from 1 to W, W being the number of periods, we say subtract I from T, so move to some previous period, and then add it all up and divide it by W, so you just get a moving average. So your forecasted demand is basically just directly mimicking the past. There are certain cases in which this would clearly be a bad idea, but there's other cases in which it might work all right. If you have a lot of growth, this is not going to be a very accurate method, but if you're in a fairly stable market, it might work. So here's another method. Exponential smoothing. It's kind of a fancy name for a process that's relatively simple. Here what you just do is you say, okay, what did we get in the last period, and then what was our previous prediction? And you kind of estimate a new prediction based on the previous prediction and the new information that we got last term, and combining them in some way. Typically it'll be a weighted average. So you got some weight W, multiply W by AT. AT is the variable you're observing. FT is the previous estimate of this, and so you give that a weight of 1 minus W, and so that shows how you update your moving average forecast. And I mean, if you have a consistently growing industry, then this would always undershoot, but it's relatively easy to understand. I mean, at least it's easy to set up mathematically in Excel. The formula is simple. And if you think about the role of the weight variable, if you have a high weight variable, that will make this estimate ft plus 1 rather stable. If you have a low w variable, if you have a high w variable, that can make it somewhat unstable if the AT are volatile. So then, when W is really high, then your prediction would closely track whatever your most recent experience had been. So either too high or too low a weight could cause problems. Okay. So here's another example. This goes through just one. Well, no. Hold on. Yeah, this goes through 5 years, 6 years actually, 6 years of data. Counts the number of new housing starts, and because of the way they've drawn this, you can kind of see something about what the patterns are. It's somewhat obvious in 1999. The second quarter was weak. In 2000, the first quarter again was strikingly strong, much higher than the other parts of the year. And the first quarter was stronger than the 2 quarters following in 1999 as well. So it seems to be a pattern that the first quarter has a little bit more in terms of housing starts, the second quarter a little bit less. Well, you can imagine why this is. I mean, there's some times of year that might just be more conducive to people buying houses. For one thing, if part of the pleasure of a house comes from the gardens and flowers and how nice it is to be in the yard and the springtime and all that, that may be easier to see in summer when all the flowers are blooming and all the trees are green and so on, than it would be in winter. So that might create a bias against the second quarter. There can also be tax reasons for wanting to buy around the beginning of the year. So that could also be a factor. But for whatever reason, there seems to be clearly seasonal variation in new housing starts. Now, if you use moving average forecasts, in fact, in both of these cases, you choose the W. So for the moving average forecast, W represents the number of past turns that get incorporated into the estimate, and for exponential smoothing, it determines the weight of the most recent observation. I guess if you have a high W in exponential smoothing, then that would cause it to be more volatile and sensitive to the very recent occurrences, whereas you'd have the opposite tendency in the case of exponential smoothing. A high value of W there would make your sequence more volatile, more responsive to whatever the most immediate bit of evidence was. We already have, I guess, a couple of projection methods. Well, you might be interested in which ones work best, and we can kind of get a rough idea of that by looking at past data and at how these two forecasts have performed. So, in this case, we say, okay, 3-quarter moving average, 5-quarter moving average, how accurate are your predictions, and how do you compare the predictions from different projects? So in this case, then, the 3-quarter moving average seems to generate larger errors. So this is a measure of the error, the observed value minus this forecast. So 5-quarter moving average works a little better in this case. Reduces the difference between the actual and the forecast. Okay, now we can look at exponential smoothing, and again, it's not just that we have offered moving average and exponential as options, as well as a moment ago the seasonal adjustment method, but also that you can choose different values for these parameters. And theory doesn't really make it clear which one should be preferable. So, let's suppose you choose W equals 0.3. Well then, if we follow this through, we get that the deviations of A from the forecast squared add up to 87.19. In the case of W.05, they add up to 101.50. So which of these methods is better? Well, just sort of crudely glancing at it, it seems like in this case W equals 0.3 would work better, but at least that gives you a glimpse of how you might go about deciding what values of those variables to use. So, Lumber seems to be an industry that uses exponential forecasting, and in this case, you notice that forecasting W equals 0.7 actually works better. Actually produces estimates that exhibit a smaller deviation from the standard. Root mean squared error. So this is a method of sort of testing, measuring the accuracy of a forecasting method. How good is the forecasting method? Well, every forecasting method is going to, every application of at least, is going to involve some n, some value of the population. It would value some AT minus FT, some profits that are squared, and then and that gives us what's called the root mean squared error. And this then can be used as kind of a crude test of the validity of different forecasting methods. That's all for now. I might return to it in another